The idea that our gut could detect disease before we consciously feel sick is no longer far-fetched. It is increasingly supported by emerging evidence from neurogastroenterology, immunology, and microbiome science. At the heart of this possibility are neuropods, the specialized, neuron-like gut epithelial cells that act as rapid sensory relays between the gut lumen and the nervous system. Traditionally viewed as nutrient sensors involved in appetite and food choice, neuropods are now being investigated as potential early warning sentinels, capable of detecting biochemical and microbial changes associated with infection, inflammation, or even cancer, long before symptoms manifest. Neuropods reside within the intestinal lining but connect directly to the brainstem via synapse-like contacts with the vagus nerve. They do not simply wait for food molecules. They are exquisitely sensitive to the gut's chemical microenvironment, which includes microbial metabolites, immune mediators, toxins, and abnormal cellular products. This allows them to detect subtle shifts in the gut's internal chemistry that may indicate a growing threat. Their location, right at the front line between the body and the microbial world, makes them ideally positioned to serve as biological smoke detectors, alerting the nervous system to danger while disease is still in its invisible, subclinical stage. Consider infection. During the very earliest stages of a bacterial or viral invasion, microbial patterns such as flagellin or lipopolysaccharide LPS interact with receptors like TLR5 and TLR4 expressed on enteroendocrine cells and neighboring immune cells. Neuropods may respond to these early pathogen-associated signals not with inflammation per se, but with neurotransmitter release, especially glutamate or serotonin, that travels up the vagus nerve to the nucleus tractus solitarius in the brainstem. This neural activity could prompt early behavioral changes, fatigue, appetite suppression, increased vigilance, all of which are classic sickness behaviors that typically precede overt fever or digestive distress. In this light, the gut-brain axis may not just be a reactionary pathway, but part of a preemptive sensory network that helps the body prioritize defense over digestion in the face of unseen threats. Inflammation offers another intriguing possibility. In conditions like inflammatory bowel disease, IBD, it has been observed that vagal tone drops well before flare-ups occur and that microbial composition shifts toward pro-inflammatory species. It's conceivable that neuropods are detecting this change in the microbial fingerprint, or sensing immune signals like interleukin-1 set, TNF-A, or prostaglandins, and relaying them to the brain. Indeed, studies show that vagus nerve signaling can modulate systemic inflammation via the inflammatory reflex, and this reflex may be initiated by gut-sensing cells before any physical symptoms, like pain or diarrhea, arise. Even more speculative, but no less compelling, is the idea that neuropods might detect early tumor activity in the gut. Cancerous cells often secrete unusual peptides, metabolites, and growth factors that deviate from normal metabolic processes. The local microenvironment becomes hypoxic, acidic, and immunologically altered. While we don't yet have direct evidence that neuropods respond to such cues, we do know that some neuroendocrine cells show changes in gene expression in response to neoplastic transformation, and that tumors in the gut often correlate with changes in appetite, satiety, and mood long before diagnosis. Could these behavioral changes reflect early neural feedback from neuropods sensing malignancy at the microscopic level? It's a hypothesis that deserves close exploration. What would it mean if the gut truly could sense disease before symptoms? The implications are profound. It would transform our approach to diagnostics, from passive detection based on patient complaint to active neural monitoring of early biological disruption. Devices that record vagal nerve activity or decode neurotransmitter signals from the gut might function as real-time biosentinels. A sudden drop in serotonin from gut neuropods, for example, could signal an impending inflammatory event. A shift in vagal signal pattern might alert us to a hidden infection or precancerous change. Eventually, this could lead to a new class of neural biomarker-based diagnostics, non-invasive, continuous, and deeply personalized. Of course, this vision is still emerging. We are only beginning to understand how neuropods interact with immune cells, how they prioritize signals, and whether their activity is disease-specific or generalized. But what is increasingly clear is that the gut is far more than a digestive tract. It is a neural observatory, continuously surveying the microbial and metabolic terrain, and potentially a key player in future systems of predictive medicine. If proven, the gut's sensory capacity could become as critical to diagnostics as a thermometer or MRI. In time, neuropods may help us listen to the body before it cries out in pain, offering a quieter, earlier voice of warning from deep within.